What are fractals? Let's go back 300 years for the work of preceding mathematicians. Fractals began in the 17th century when Gottfried Leibniz pondered the concept of self-symmetricity, in which he thought only applied to lines. It wasn't until 200 years later Carl Weierstrass, the father of modern analysis, presented a function that was continuous everywhere but differentiable nowhere. We now know this to be a fractal. Other contributions to the development of fractals include George Cantor with his Cantor sets, Felix Klein and Henri Poincare with their self-inverse fractals, Helge von Koch with his more geometric representation of fractals called the Koch snowflake, and many more. But today we will outline two famous mathematicians' contributions to fractals and their application to modern applied mathematics: Development in Fractal Dimensions by Benoit Mandelbrot and the Hilbert curve by David Hilbert. Fractals are geometric objects that have infinite amount of detail. They look rough, even under indefinite magnification, which disagrees with calculus. When relating this to the real world, objects such as bark or shoreline are not flat or round like your traditional polyhedrons or spheres. As we zoom in, we can examine so many crevices and intricate detail it would be impossible to model the natural world with our traditional shapes, as most things in nature exist rough rather than smooth. Self-similarity is a property of certain shapes that describes when a shape, for example a square, is divided into smaller equal sections of the same shape. Each section can be enlarged to the original. There is a common scaling property in fractal dimensions which applies to self-similar shapes. It describes that the amount of mass or space a shape holds when it is scaled up is proportional to the scaling factor increased to the power of the number of dimensions that the shape is resided in. There will be a written example of this later. For non-self-similar shapes like shorelines, a box counting method is used with precision to yield their fractal dimensions. Other than ordinary shapes like squares and cubes, most fractal dimensions do not have integer values. They come from shapes in nature which are mostly not self-similar or even smooth. This creates motivation to study such shapes as they have various degrees of roughness.
In the real world, an application of fractals is in medical imaging. Cancer researcher Dr. Larry Norton said tumours have higher fractal dimensions than normal tissues, indicating their greater internal complexity. Here is a written example of the Sierpinski triangle. When we scale the size of the Sierpinski triangle by a factor of 2, which is the same as magnifying the triangle by a factor of 2, the magnified triangle is just 3 copies of the triangle, each with an infinite amount of detail just like the original due to its self-similar property. We can note that the mass of the magnified triangle is scaled up by a factor of 3, equals the magnification factor 2 raised to the power of its fractal dimension d. Now we take the natural log of both sides, ln 3 equals d ln 2, d equals ln of 3 divided by ln 2, and d equals 1.58. What's the most efficient way to fill up a 2D space with a 1D line like in a game of Snake? Turns out the way to do it is with a Hilbert curve. The Hilbert curve was discovered by David Hilbert in 1891. When several iterations of the pseudo-Hilbert curve is applied, we achieve the Hilbert curve where each point approaches a fixed point. Why is this useful? Well, let's consider sorting 1D data into a 2D space and how will we go about it. We could do it like this snake curve GIF, but when we want to upgrade this storage device, our data will be at different points in space, making it hard to locate where the specific data point is. This isn't very processing efficient. If we were to use a Hilbert curve, our data points would approach a specific coordinate with every upgrade or iteration. Organising IP addresses in the worldwide net is done this way. Randall's map of the internet shows how the IP addresses are organised.